call it.
Hello, everybody. Welcome to this month's Future in Space Hangout. My name is Tony Darnell, and I work at DeepAstronomy.com, soon to be DeepAstronomy.space, I think. But anyway, that's a little bit in the future. And today, I love it when we get a chance to talk about the Hubble Space Telescope. I can't say, and I love talking about this amazing instrument that's been up in orbit now for 27 years. And so it has, I am not overstating it when I say it has fundamentally changed the way we look at the universe. And so I'm very excited to be able to talk about this. And since this is a Future in Space Hangout, we're going to be talking about the future of the Hubble Space Telescope. We'll also get some background and stuff like that in there as well. But, you know, you've seen many hangouts on Hubble, many of you have. So we're going to concentrate on the future, what's in store for the Hubble Space Telescope, and we hope that you will be able to ask us some questions and comments to our guests, because we've got all the Hubble rock stars here today, folks. So this is your chance to talk about them. And I'll introduce my guests here in just a minute, but before I do, let me start with my co-host, Dr. Alberto Conti, from his very luxurious office. Hi, Alberto.
Hi, and it's not my office; it's my home.
Yeah.
That's why it's luxurious. So, hi, Tony. It's great to see you. A shout out to Harley, who couldn't make it today.
That's right. Harley Thronson, who normally puts these together, could not attend this particular hangout. So we do miss him, but Alberto is here for us again. And he is the innovation scientist at Northrop Grumman, who is building, I think, I know, the successor to the Hubble Space Telescope. So welcome, Alberto. It's good to see you again. I'm glad you're here.
Good to be here.
And this is a live event. We're here. We're here right now. And so what that means is that we would like you to interact with us and ask us questions, leave us comments. There's many ways you can do it. The best way is to go to deepastronomy.com/live, where I have a live chat client set up right now. Many of you are already typing in things, and I'm seeing them scroll by. There's also the live chat on the YouTube channel, the watch page that this is on. I'm also looking at that, and that is also scrolling by rather furiously as well. So those are two ways you can leave comments for our guests or ask questions to our guests. And also, I'm looking at the Future in Space hashtag on Twitter. So we hope you can also leave comments that way as well. So let's get to our guests. We have a lot of really great ones today, all of them working on the Hubble Space Telescope project, starting with Dr. Jennifer Wiseman. She's a senior project scientist for Hubble at the Goddard Space Flight Center. Welcome, Jennifer. I'm glad you can make a hangout for us.
I'm great. Glad to be here.
Good. Thank you. And also joining me is Dr. Olivia Lupie. She's the HST Instrument Mission Operations Manager at the Goddard Space Flight Center. She also was responsible, and this is going to interest you guys, she also works on these, what she's calling the life extension initiatives for Hubble. I can't wait to learn more about that. So welcome, Olivia.
Thank you very much, Tony.
Also, my good friend and colleague is joining me, Dr. Carol Christian. Hi, Carol. She's here as a guest today. What is that? What is that?
It's a magic. It's a magic ring.
Oh wow, that is.
That won't help you.
I hope you. Okay, don't. That's Carol. That's Carol trying to give me a. Okay. She is
matches the color of her hair.
As many of you already know, she is the Hubble project scientist for outreach at the Space Telescope Science Institute. So I'm glad she's here. She is here also to tell us about Hubble. And finally, last but certainly not least, the rock star of all rock stars on working on Hubble images, Zolt Levay. He is the we tried to figure out what to call him, in the hangout before it started. We settled on science visualization developer, but none of us really like that, so we're calling him the Hubble image guy.
Hubble image guy is a good idea.
The Hubble image guy. He makes some of those beautiful images that you see on the press releases, as well as the posters and everything else that you see everywhere. Hi, Zolt. It's so good to see you again. Welcome back to our hangout.
Hi, Tony. Thanks for asking me. It's great to be here. And hi to all the other guests and everybody else out there.
Yes. So, okay. Well, let's get started. I think I will start with you, Jennifer. Can you give us, or should it be Olivia? I forgot what we said before the hangout started. I want a current status of the Hubble Space Telescope. How is it doing today?
Well, I can give a status on the operations.
Okay, go ahead,
Jennifer
Olivia.
can give a status on the science performance. But Hubble is performing beautifully. The Hubble is a spacecraft as well as an observatory, and so it has a spacecraft parts, meaning pointing or attitude control, power systems, and communication systems and so forth, in addition to the telescope and the science instruments. And all are performing beautifully. We have no degradation in science performance because something else isn't working. And, our solar arrays are producing more than enough power than we need, and the batteries are working better than they were predicted, as are some of our science instruments. So that's in a nutshell. We're doing terrific. So I'll hand it over to Jennifer.
Okay, Jennifer, give us an update on the science of Hubble. How's it going?
Well, that is hard to give in a nutshell, but I will try. Hubble is exceeding anyone's wildest expectations on its science return. I mean, here we are, almost 27. We're almost about to reach the 27th birthday of Hubble, and yet it is as scientifically powerful now as ever. I mean, I'd say it's more scientifically productive now than ever. And so we are reaping wonderful science rewards right now. We're glad, as Olivia mentioned, that all the science instruments are working very well. So we have more than one camera on Hubble and more than one spectrograph, and that's giving us a lot of flexibility so that we're able to study everything from dynamics of our own solar system to what's happening in the very distant universe. And scientists are using Hubble in very creative ways, which I think I'm sure we'll discuss during this hangout. But in a nutshell, Hubble is very scientifically productive right now for both our solar system and the distant universe and everything in between.
Okay. I want to remind, this just occurred to me right now, and I want you guys to do this on the live chat. And I'll read it toward the end of the hangout. Give us what is your vote for your favorite thing Hubble ever did, or you could say what your favorite image is, or any kind of Hubble memory. I'm going to go through the chat and we're going to read some of those toward the end. I want to know what you guys think about this thing, because as both Jennifer and Olivia said, this thing has beat everybody's wildest expectations. And I think part of that, Jennifer and Olivia, and even and Carol, you can comment too if you like, the fact that this is not the space telescope that we first started with, is it? This had the luxury of being repaired over the years, right?
Yeah, it's been repaired. Well, Olivia can speak more to this, but it's been serviced several times since its launch in 1990. And the latest mission that we serviced it on, SM4, a few years ago, 2009, has left the telescope in superb condition. But Olivia, you might want to expand on that a little bit.
Sure, I can. Tony, could you put up the chart on the Hubble servicing missions that you liked?
I'm doing it now. Just go ahead, and I have it up now.
Okay, terrific. So in this chart, you can see we launched in 1990, and then we had 5 servicing missions since then, where the astronauts on the shuttle went and grappled Hubble, put it in the shuttle bay, and then performed replacements of components or subsystems, repairs of subsystems, so forth. And so on this chart, you can see in servicing mission 1, we put in a new camera and the corrective optics for the spherical aberration. In servicing mission 2, we put in the imaging spectrograph, the infrared camera, fine guidance sensors. In SM3A.
By the way, we're celebrating the 30th anniversary of that servicing mission and of the installation of the STIS instrument, which we're still using. So we're real happy about that. But carry on there, Olivia.
Fantastic. Thank you for bringing that up. And then in 1999, we put in the advanced camera for surveys and a new fine guidance sensor. And in SM3B, which was in 2002, we put in the advanced camera in 2000.
Hold on, Olivia. Let me just stop you for a second. We're hearing an echo coming from someone, and I don't know if it's you or not. But can everybody just maybe turn down their volume a little bit? What's happening is the speakers are going back into somebody's microphone, and we want to make sure we don't get that echo. Trying to figure out. I don't want to have to mute everybody to find out who that is. Hello?
Hello?
Okay. Yeah.
Okay, so I won't belabor this, but you'll see that we've replaced the gyros a lot, and we can talk about that a little more later. But if you focus on SM4, do you still hear the echo?
Yeah, Fred, I do. Let me just mute you for a second, and then you can unmute yourself to finish. Hold on.
Or if you have headphones,
Testing,
Olivia,
1, 2,
yeah,
3. Yeah,
earbuds or headphones.
It's
that would
Olivia,
help.
I'm afraid.
Yeah, earbuds will really help.
Yeah. So that's what it
Well,
is.
while she's looking for earbuds, let me
Okay.
correct myself. I think I said it was the 30th anniversary of STIS. That would be.
I know, I was
Telescope has
It
been-
is 20. It's 20.
It's 20. What we're also celebrating, though, is the anniversary of the control room for the Space Telescope Operations Control Center at Goddard Space Flight Center, which did open up before launch. So we are celebrating multiple anniversaries this week.
Okay, so you were just talking about how Hubble did have the benefit of being completely new telescopes put up each time it went, new instruments, new cameras, new wavelengths were made possible by the Hubble Space Telescope, which was responsible in no small part for all of the amazing discoveries, because it was evolvable. It was one of those things that we're starting to hear a lot more about now, evolvable space telescopes. These are things that can be changed over the course of their mission. And so with Hubble, it's had the luxury of had that happen many, many times. But I have a question. Is in CoStar, the corrective optics for the spherical aberration, is that still on there? Because that was on the primary mirror, right?
Yeah, you can see that in a museum now, but maybe
Yeah.
Olivia can extrapolate a little, or
you
Carol
should-
can talk a little bit more.
You should come back to Washington, D.C. and see it in the Air and Space Museum.
Okay, so when
They're on display.
so how is that corrected? They didn't put a new primary in, so how did they fix that?
Because every instrument has a correction.
Okay. Very good.
Yeah, no, CoStar was removed.
Okay, I'm still hearing the echo, unfortunately, Olivia.
Okay, let me see what I can do. Go ahead.
All right.
Just Olivia, if you can turn off the volume of your laptop so that the only way you hear it is through your earbuds, that should work.
It's funny how it always does this right when the Hangout starts, and then we don't have, because we test for it before we go, and we don't hear it until we start broadcasting, then we do.
Yeah.
Okay, well, all right, so we've got, I'm still hearing it, darn it. Okay, so we are, yeah, I'm just going to start muting, and then we'll unmute if you go to talk. Okay, so there. Now it's gone. Okay, so sorry about that, folks. If you want to, if you guys want to join in and just unmute yourself, and then we'll mute it again later. Is the way we're going to have to work on this. So we are talking about the Hubble Space Telescope's past. It's currently very healthy. It's doing a lot of great work, and a lot of good science is coming out of it. But Zolt, can you give us some idea and what is it like? I mean, over the course of the years, first of all, I want to know, how long have you been working on the Hubble Space Telescope?
Well, I've been here at the Institute since before launch. I started here in 1983. I was working on some support software before launch, and
83. Okay.
1983.
Wow. So
a long time. Yeah.
You definitely have. Wow,
But
that sounds like about as long. Carol, you've been around that long too, right? I mean, it's on the mission about.
No. I was on another wee mission called the Extreme Ultraviolet Explorer. I've only been here a short 20 years.
Oh, okay, only 20 years. Yeah, that was okay. So give us an idea of what it's like working with the images. What are the images that come to you like, and what do you have to do to make them look the way that we all see them?
Well, I'll just say that it's been a real privilege and honor for me to be able to work on this mission. It's a very high-profile mission, obviously, and the science, is world class. But we use the science data. We don't get anything special from the telescope. We get the same data that the scientists use to do their analysis, and since they're imaging instruments, we get to make images from them. The only catch is that the cameras don't make color images automatically. So if we want to use the color information that's coming from the light that the instruments record, then we have to manually reconstruct them as color images. But that's a pretty straightforward process. It's the kind of the same process that every color technology uses to assign colors to different channels and reconstruct the images. So we simply take the images and we do some, there's some objective things that we do, some more scientific things we do to produce the images, and there's more subjective things we do to produce the images to make them more interesting and more visually powerful.
So I was just going to mention the reason that they don't come in color is because the scientist wants to know, investigate different astrophysical phenomena. So for example, if you want to look at a galaxy and you want to know whether there are blue stars and red stars in it, then you need to sample blue, green, and red, for example, simplistically. So each image is taken with a specific filter, usually pretty broad filter that lets a lot of energy through. For some of the beautiful nebula that we process, you might want to know very specifically, oh, is the nebula producing carbon emission? Is it producing nitrogen emission or hydrogen emission? And then you use what's called a narrowband filter, where only that particular element can be detected. And that produces a different result, so the scientists can figure out the different astrophysical phenomenon. And then what happens is that the scientist analyzes that data numerically and through modeling, and Zolt then takes those images and make them into the beautiful imagery that you see. Okay.
And so Olivia, I want to ask you about what current images are on Hubble, I'm sorry, instruments are on Hubble right now.
Okay. The science that Hubble is doing right now is a program to get the proper motion, or the motion of dwarf galaxies in the vicinity of the Milky Way, to make studies of these dwarf galaxies as seen through the halo of the Milky Way, and those observations are happening right now.
Okay, and what about the cameras themselves? What sort of cameras are currently on board right now?
Okay, we have two cameras on board, which are working very well. We have the advanced camera for surveys, which was installed in 2002, and it was repaired in the servicing mission in an amazing process that the astronauts had to cut through metal and pull out electronic boards and do all sorts of extremely delicate removal of screws. Excuse me?
Brain surgery, almost like what John Grunsfeld was saying, right? It's almost like doing brain surgery.
Like brain surgery. Anyway, yeah. So the advanced camera for surveys has a CCD, charge coupled device, which is very similar to the cameras in your iPhones, although the ones on Hubble are a lot more expensive and a lot more sensitive. And it primarily does observations by studying the visible part of the spectrum and the ultraviolet, some of the ultraviolet, but it's optimized for the visible, the light that we can see with our eyes. It also has an ultraviolet camera called the solar blind camera, and that blocks out solar light. We say solar light, or light of wavelengths greater than 3,000 angstroms, the light that is emitted by the sun. So it's looking in the ultraviolet. The Wide Field Camera 3 was installed in 2009, and it is the most sensitive camera in astronomy, definitely in space. And it is composed of a CCD channel called the UViz and an infrared channel called the IR. And the infrared, it's only in the near infrared. It will certainly not go to the longer part of the infrared range, as will JWST. So those are the cameras that we have on board, and each of those cameras has filter wheels. As Zolt was talking about, looking in single colors, astronomers need to use filters to block out every other kind of light but the light they want to study. So we have blue filters and red filters. We have narrowband filters, in the visible and the ultraviolet and so on and so forth. So those are the 2 cameras that we have on board. And Wide Field Camera 3 is just performing, better than predicted at this stage, even after 8 years in orbit.
Okay, and so I'm going to put this up real quick, Zolt. This sort of underscores what Olivia was just telling us about the different wavelengths that Hubble can see. Wait a minute. Why isn't it? There it goes. It's doing it on my. Hang on.
Broke it.
I broke the internet. Hang on. Let me just. I want to. Oh yeah. Here we go. Sorry, wrong window. There we go. So tell us a little bit about this image, Zolt, and try to couch it with context of what Olivia was just telling us about what Wide Field Camera 3 can see in the infrared versus what we're looking at here.
So, okay, I'm not actually seeing the image.
Oh, you don't?
No, yeah, I can see it. Just click on.
You might have to refresh your browser.
Yeah.
Sometimes it gets hung up.
We can see it.
Oh, he hung up. All right. Well,
you should ask your questions more politely.
Okay. What do you mean more polite?
Yeah.
Okay. So here we are. Maybe Jennifer, you could talk a little bit about this image here.
I don't know how to unmute myself.
Sorry,
I can speak.
There's
Zolt.
Oh, there's. Okay.
Okay, sorry.
I'll let you talk to it. Yeah.
Yeah, so we're seeing 2 images of the same object. This is the more or less famous M16 or Eagle Nebula. It was first imaged by Hubble back in 1995 with the previous camera, the Wide Field Planetary Camera 2, sorry. And this new image was taken a couple of years ago with the Wide Field Camera 3. That has 2 channels in it, a visible light channel, as Olivia was describing, and an infrared channel. So we're seeing the same region of sky taken in light that we can see, in visible light, and that's the more, the pillars which you see more strongly and the fewer stars. In the infrared light from the stars is able to penetrate the dust in this nebula, and so we're seeing many more stars show up, and the dust is less apparent in the nebula, so we're seeing the pillars not completely disappear, but much fainter.
And Carol, this goes a little bit to your point earlier about what science needs to get done, right? On how we, what filters we use, things like that. I mean, what you see in the infrared is a lot different than what you're seeing from the sort of visual light part, right?
Right, and so one of the questions when the visible light imagery was taken of the pillars was how many stars are actually embedded in those clouds, and what do the pillars represent? So we notice in all kinds of star formation regions that there's gas and dust clouds, the stars start to form, and then they start to push the material outwards and they run into other material. And so the question was, in the tip of each one of those pillars, are there stars forming? Is it intense dust? And there's no real way to figure that out unless you're able to observe pretty much with a similar resolution, but in the infrared, so you can penetrate that dust as Zolt was describing.
And I didn't realize this until Olivia was talking about the wavelength ranges of Wide Field Camera 3. You're doing the same image. The CCD on that camera is sensitive enough to do UV all the way down to infrared. Did I hear that right, Olivia?
No, you didn't.
Oh.
No, I didn't say it right. There's 2 separate detectors. One is the UVIS the UVIS channel, which is a CCD detector, which is used for ultraviolet and visible.
Okay,
yeah, I'm sorry.
No, it could be that I just misheard it, because I thought the same camera was doing both wavelength ranges.
Right. These both instruments are in the wide field camera, but it consists of an IR detector channel and a UVIS detector channel.
And Carol, as you pointed out many times in the past, to me, that I learned this from you, is this Hubble's it when it comes to the UV, right? If you want to see things in the ultraviolet, this is the only game in town, because you can't do this on the ground.
Yes, and so we have a couple of years ago, in recognition that that was the case for a while, there actually has been a push to make sure that whatever we need to do with Hubble in the ultraviolet is getting done. And so there are some very interesting studies being done with STIS, the Space Telescope imaging spectrograph, and also COS, as well as the UVIS of Wide Field Camera 3. So we are looking at things now in the UV, not to the exclusion of everything else, but it is, I would say, real popular as far as what people are proposing to do.
There was another mission called GALEX, which was a Galaxy Evolutionary Explorer, which was a UV telescope, but that was very, very different than Hubble. It was a survey telescope, so it doesn't have the resolution and capability that Hubble has. And GALEX is now is not working anymore. Actually, mission ended in 2013, and so really, as Carol said, the only UV game in town is now Hubble, which is a little worrying for me because there's a lot of science, as you can, as Carol just mentioned, and others that you can do in the UV. So it would be, it will kind of behoove us to think about, the next generation of UV instruments as well.
Well,
so
that is actually.
I will give you an example that we can look at galaxies pretty much in the near universe, for example, and we would like to understand stars and galaxies in the near universe, in the ultraviolet, and we'd like to understand them in detail. We believe, we know, we have evidence that when you look at more distant galaxies, there are some similarities, but of course the wavelengths are shifted to the red. So we want to understand what we're looking at in the red. So if you look at nearby galaxies in the UV, then you can say, oh, I understand these. I think I have an analogy to something more distant that now I see in the visible or in the infrared, because it's been shifted by the expansion of the universe.
That's a great segue into what I would. So that the fact that the UV is so important on Hubble right now is a good segue into the future of Hubble, because it's not going anywhere. We are still going to be around. It's still going to be out taking these images. And I want to get to the future of Hubble in just a minute, but first I want to remind you that you're watching a Future in Space Hangout. My name is Tony Darnell, and we are discussing the Hubble Space Telescope. We've talked about its past, and we're about to talk about its future here. And my guests are Dr. Olivia Lupie, she's the HST Science Instrument Mission Operations Manager, and also Dr. Jennifer Wiseman. She's a Senior Project Scientist for Hubble at Goddard Space Flight Center. Dr. Carol Christian is also the Hubble's Project Scientist for Outreach, as well as Zolt Levay is the Hubble image guy. As well as Dr. Alberto Conti, the innovation scientist extraordinaire at Northrop Grumman. So, okay, let's talk about the future. And
well,
Jennifer,
I was wondering, Tony, if I could just add a few examples of this ultraviolet science.
Okay, by all means.
Cool,
yes, go
right
ahead.
now. You talked about the uniqueness of Hubble's ability to do general ultraviolet astronomy, and that's certainly true. And I'm just impressed by the variety of things that astronomers are proposing to do using Hubble's ultraviolet capabilities. One of the more recent intriguing observations taking advantage of this ultraviolet capabilities was a recent observation of Europa, this moon of Jupiter that is, of course, very intriguing. It's an icy moon.
There you go, I have it up.
And a few years ago, Hubble took some observations that seemed to show spectroscopic evidence for the components of water vapor being perhaps vented between the cracks in Europa's ice. This was a spectroscopic observation with the STIS instrument on Hubble, which was repaired in the last servicing mission. So I'm thrilled we're able to use it for this. And then just last year, observations were taken again with STIS, but this time looking at Europa as it passed in front of Jupiter. And so we kind of saw it in silhouette, and you could see sort of physically the evidence of these plumes coming out from the southern part of that moon. I don't know if you can show that image. Yeah, okay, so the image there, and so that's a Galileo image of the moon itself, but the plumes you can kind of see there, those are the Hubble detections, potential detections of plumes being vented from between the ice there. We have to do more observations to really confirm that that's what's being seen, but it is very telling. It's from the same area of the moon where the the spectroscopic observations of water vapor components were seen just a few years ago. So all of that's being done with ultraviolet observations with the STIS instrument, which is, again, one of these innovative ways of using ultraviolet capabilities on Hubble that just makes me so happy again that we got that instrument repaired back in servicing mission 4. And also, I'd like you, if you could put up that Jupiter image.
Yep, it's up now.
Hubble's been looking at Jupiter for a long time, and we've been able to see its changes in its atmospheric bands over time, and that giant red spot that we know is a big storm, that's actually seeming to shrink over the decades. But you'll also notice in this image the aurora up at the top, that bluish region is actually an ultraviolet observation superimposed over the visible light observation of the rest of the moon here. And with that ultraviolet image, you can see the aurora, and it's excited by action of the magnetic field and charged particles around Jupiter. Jupiter has a very powerful magnetic field. So by having this multi-wavelength capability on Hubble, we're able to see both its visible atmospheric features as well as these ultraviolet features of its aurora. In fact, on our website, if you look to hubblesite.org, you can actually look at this and see little videos of the aurora dancing around as we look back at it over and over again. We did this observation and continue to in sort of conjunction with the Juno mission, the probe that's arrived at Jupiter and is doing all kinds of studies of Jupiter's environment, including its magnetic field. So while that in situ probe can study the magnetic field, we from afar with Hubble can look at the impact of the magnetic field and charged particles on the aurora and see how all this works together. So I really like the way Hubble's being used to interact with other missions and probes, and also how we are using this ultraviolet capability to do really innovative observations.
But also, I think what you just said, Jennifer, is great, but also underscores the fact that by looking at across the wavelength spectrum, from the UV to the visible to the infrared and so on, we get a tremendous amount of information about all the processes that are ongoing. And I think that trying to get the panchromatic view of either planets or stars or galaxies is something that is, at the core of the science that we've been doing for the last almost 30 years with Hubble, which is fantastic.
Yep. And so I'm just reading some, as you guys were talking, I was reading some of the comments. There were people are mentioning things. I love Alberto's JWST wall clock from Philip W. And we wish there was a way to preserve Hubble. So I want to. So Jennifer, you talked about ways in which Hubble is working with other missions. You mentioned Juno. It's also involved in, it was involved in the New Horizons mission as it flew by Pluto, right? Can you make a few comments on that as well?
Sure. So Hubble was a really important part of the planning and execution of the New Horizons mission, the probe that recently passed by Pluto. Hubble did observations of the Pluto region and discovered actually several moons that had not been discovered before around Pluto, and that was interesting in its own right, but it also kind of helped the mission planners for New Horizons to chart the best course for that probe. And now Hubble has been used to look beyond Pluto and out in the Kuiper Belt to look for potential targets that New Horizons probe could potentially investigate now that it's past Pluto and continuing its journey outward. And in fact, we have found a good candidate object, just a tiny rocky body out there that New Horizons will potentially be able to visit. So that's another way of using Hubble in conjunction with other missions. We're also using Hubble in complement with other telescopes that are currently functioning, like the Chandra X-ray telescope, other space telescopes like Spitzer, which is an infrared telescope operating now. We are doing complementary work with ground-based telescopes like ALMA, and we're certainly preparing for the James Webb Space Telescope. We already have a special category of Hubble observations that are called JWST preparatory science. So we're doing things with Hubble, learning as much as we can using the capabilities of Hubble to prepare for the kinds of science experiments and observations that scientists want to do with the James Webb Space Telescope. Hubble is in such good shape now that we actually are confident that both of these major space telescopes, Hubble and the James Webb Telescope, will be operational at the same time, overlapping by at least a couple of years, maybe several years, and that's going to be wonderful. So we're both doing preparatory science for James Webb, and then we're thinking about what we can do when we have both of these observatories operating at the same time, which will give us, again, even expanding our wavelength coverage from the UV through the visible into the infrared, as Hubble can do, and then farther into the infrared wavelengths of light with great sensitivity, like the Webb telescope will do.
Okay, this hangout is zooming by, and I gotta get Olivia. I gotta talk about this. One of your jobs, Life Extension Initiative. That is? Tell us about that. What are you working on? What does that mean?
Well, the Hubble team for years now, since 2004, has been looking at several different ways to extend the life of the mission life of the Hubble Space Telescope. And we work on several flavors. Okay, one is kind of an obvious one. It's mechanisms. And if you can bring up the chart package that I gave you, okay. I just want to show you what I mean.
Okay, which one do you want me to show?
I want you to show the schematic of Wide Field Camera 3.
Okay, will do. Let me put this up. This was the other one. Is it? I believe is it that one? No.
Nope. Keep going back. Keep going. Oh, it's the one that got corrupted. I'm sorry.
Oh,
well, why don't you put up? Why don't you put up the one with the astronaut holding Wide Field 3? Not that one, but a previous one. Yes.
There you go.
Okay, so I'm sorry. I had the innards of Wide Field 3 to show you. This, by the way, is from Servicing Mission 4, and Space Telescope's on the left there, and it's sitting in the shuttle bay, and one of the astronauts has got the old Wide Field camera, which looks just in shape, just like the Wide Field Camera 3, but it is removing the old camera, and you can see. Do you see my words there that says Wide Field 3 inserted into HST?
Mm-hmm.
Okay, that's the Wide Field Camera 3 inserted in HST. So that gives you a feel, for about how big. That's the radiator outside. What I wanted to show you inside, and all the science instruments have this, are mechanisms. And you can imagine that mechanisms wear out after continued use. Now, the mechanisms are designed to last for thousands and thousands and thousands of rotations, but nevertheless, we still want to use them and use them efficiently so that we don't add more and more motions than we have to. But we also don't want to impact the science. We don't want to, say, don't use this mechanism this much, so you can't use this mode. No, we want to maintain the efficiency and the capability, but our engineers are very innovative and creative, and they find ways to use these mechanisms wisely. Okay, and so, what I was going to show you is that the Wide Field Camera 3 has two filter wheel mechanisms, one with 6 filter wheels on it. It has a focus mechanism, and it has a channel select mechanism. The spectrographs also have filter wheels and grading wheels and so forth. And in fact, on the spacecraft itself, I got to put myself up here so I can see what you're seeing. On the spacecraft itself, there's a lot of mechanisms. Okay, here we have the solar arrays. Okay, these are solar arrays on these booms here, and as the telescope points, they have to rotate to stay face on to the sun, or nearly face on to the sun. So there's a mechanism there, and one of the things we did was, well, these produce almost twice as much power as we need. So we don't need them always exactly face on. So if they're a little bit off angle to face onto the sun, that's okay. That's how we preserve the mechanism, and high gain antennas and so forth. So
you're worried about things, if I'm getting what you're saying right, you're worried about things that are moving around a lot, things that have to go in and out of optical paths.
Yes.
And even the solar arrays, which you say don't need to be as directly facing the sun, that would increase anything that can increase the life, right?
Yes. And now that's only one kind of category that we've implemented a lot. And for Wide Field Camera 3, for example, the motion of the channel select mechanism has been reduced considerably just by redesigning some of the calibration proposals that turn the wheels a lot. Okay, so, but there's also another category, and this category, the Hubble team anticipates the aging or failure of certain of the high-risk components on Hubble. And by anticipating that failure, we can prepare in advance the procedure, the methods of how we recover from that failure, how we get back to science. For example, we've prepared, the Hubble Space Telescope has 6 gyros on it. We need 3 for nominal operation. But because our gyros are very sensitive and they have failed in the past, our engineers have created a 2 gyro pointing control mode where only 2 gyros are needed, and a 1 gyro pointing control mode using only 1 gyro. So, and we're very close to being ready to just, and I want to say we're not going to, you know, if we lose all our gyros tomorrow, except for 1, it's going to take a while for us to get on 1 gyro science. But the point is, we've done months and months, even years of preparatory work so that when that happens, if it happens, we're ready. Now, on 1 gyro science, we are going to lose some capability, some efficiency, scheduling efficiency will be less robust to disturbances.
What do the gyros do? Or why don't you tell us that they're important?
Oh, I'm sorry. Yes, gyros are sensors. So the Hubble Space Telescope has no thrusters. It has no propulsion. And so, you know, when you want to move, when you want to turn the Hubble from pointing over here to over here, okay, it has to do so using reaction wheels, which are wheels that accelerate and decelerate, spin up and down, and conservation of angular momentum, you can move the telescope. So that, and they also keep the telescope stable. Now the gyros are sensors, and the gyros sense the motion or the angular motion of the telescope around different axes. Okay, there's, you know, we use 3 gyros, we have 3 different axes. So the gyros sense the telescope motion. And when you're pointed on a target, you want to be absolutely still. And still for Hubble is freaking amazing. It's really still.
Freaking amazing.
So,
I like that.
Anyway, so the gyros are devices that have a spinning wheel in the center, and they're mounted on a float, which floats in a liquid. And so the gyros then can detect the smallest motions in a specific direction, and they feed that information to the main computer, which has very complex programs that says, oh, I see, we've moved a little this way, and now this is done really fast, 40 times a second. But the computer program will say, oh, I see, we've moved a little bit, so we need to move back. And so it sends the appropriate commands to these flywheels, these reaction wheels that I was talking to before. And that's what gyros are, okay? And so these gyros are the most sensitive, and they give us the incredible spatial resolution that Hubble has. But we have had failures with them. They're delicate, and you know, we do a lot of things to work around that. So I forget what I was talking about before, but we built we have a 1 gyro science mode prepared in advance and a 2 gyro. Now the other thing we also did was our data management system inside the Hubble, and each of our science instruments are built with 2 powertrain sides and electronics. So there's redundancy built into the instruments and to some parts of the spacecraft. Now the mechanisms in the instruments are not redundant, but the electronics that drive them and the power is redundant. So if we should have, and as we have had in the past, if we have a component failure that shorts, and that on one side, we can perform a switch or transfer to the other side and bring the science instrument up to the other side. And we have all the procedures and prepared for that, and the Space Telescope Science Institute has all the calibrations that would have to be done if we had to do that. So it's all prepared, all for the sole purpose of getting back to science as quickly as possible, to maximize science in the near term while finding ways to extend Hubble's mission in the long term.
Okay, so
And the last thing we have is what we've done are onboard protections. We have enhanced our onboard autonomous protections against failures. So we have a whole slew of things that we've done, and I can go on and on and on, but
okay.
I'll stop there and
well, very good. So I guess I don't know how people do it, to be honest with you. I know that if I were in that Hubble control room, I don't want to touch anything. I mean, it sounds like what you guys are doing is handling it with kid gloves, and that's very good. You don't want to wear it out faster than you have to.
Right.
What keeps you guys awake at night? Does anything worry you guys about this? About anything worry you more than others as far as the operation of Hubble? Anybody?
Well, the gyros, of course, because like I said, we've had trouble with the gyros, and we're monitoring them very closely, and we can see them aging. And a lot of parts on Hubble were built in the 70s, and yes, they're working perfectly now, but many of these parts, many of these subsystems are way beyond their life, the lifetime that they were built to, right? So
one more
everything's looking
testament
beautifully, but then you're always worried about some of these older components.
One more testament to the quality of Hubble over the years. So that's really good.
Yes.
All right. Well, it came out this week. There was I just want to mention this briefly. Some people are, well, before I get to that, so Olivia, you're doing all this work. You're taking care of Hubble. You're operating it, but you're being smart about how you operate it. You don't want to turn the filter wheels more than you have to. You don't want to move Hubble around more than you have to. You certainly don't want to articulate things that articulate too much. How long are you expecting Hubble to be up there?
Well, that's a great question. And I just wanted to clarify one thing. It's not me that's doing all of this. We have an incredible
part of the team you're thinking about
and science team at the Institute and here at Goddard. So, all the kudos go to them. But
I tried to give it all to you when you tell you.
Yeah, but that's okay. I can take it for today. I'll pretend. The lifetime predictions, and we do perform. We and another group at NASA performs lifetime predictions based upon how long a component has lasted and what the history of that performance of that component is, and so forth. And we're looking to the middle of the 2020s here, where the probability estimates show that we should be producing a really good science until 2020, and then probably really good science until the mid-2020s, like 2025 or so, even beyond. For example, I'm looking up here, I can't show you this, but the predictions for the gyros, like I told you, well, if we use 3 gyros, which is the best attitude stability, if we use 3 gyros until we only have 2 left, and then use 2 and then get down to 1, we'll have at least 1 gyro. We have 90+% probability of having at least 1 gyro through 2025. All right, and again, these are very
2025. That's the lower. So that would be what? Just that's a hard limit. Beyond that is probably Hubble will probably decay or.
Oh no! These are not hard limits. These are just. I just gave you the probability of the wear out of the gyro as a component. Okay, the science instruments, wide field camera and 3, and the cosmic origin spectrograph are predicted to last 98% probability to be performing well in 2025.
So Alberto, JWST is going to be launched in 2018. She's talking about JWST will be up there 10 years.
Exactly.
We
Isn't that
are
amazing?
gonna be here. We are gonna be here.
But that's amazing for the science we're going to be able to do. Come on, it's going to be incredible for the things we're going to be able to do. So
absolutely,
very exciting, very very exciting.
And Jennifer, I just got to ask what Olivia has been outlining to us with the future and what she's doing with operations. How does that influence your thinking about the science? Do you guys plan ahead and go, okay, well, we only have a couple of gyros now. This is the kind of science we're going to do. So we're going to look. We've talked in the past in these hangouts about how Hubble time is allocated. So people know about the time allocation committee and things like that. But does that go into your thinking about what sort of science has priority for Hubble, I guess, is the way I'm trying to ask it. Oh, you're muted. I'm sorry.
Muted. Sorry.
I had to mute you because of the echo.
Absolutely. We're thinking about that a lot. And the Hubble mission management is in active conversation all the time with Hubble users, with scientists from across the country and around the world, to really get their ideas on how we should prioritize what kind of science we should do. Now, right now, scientists can propose any kind of science that they would like to do with Hubble, and it gets peer reviewed, and it's a pretty hefty competition to get selected. But we're also thinking of more innovative things. What should we be doing? What do we want to make sure we observe with Hubble while we still have it, so that we don't regret years later looking back and saying, why didn't we do this or that when we had this capability? So I think we're doing several very interesting initiatives. One that was already mentioned is something we call the Ultraviolet Initiative, which is to encourage astronomers to think of fruitful ways of using Hubble's ultraviolet capability while we still have it, because there are no other sort of general purpose platform observatories with ultraviolet capabilities in the near future beyond Hubble. So that's one emphasis that we have right now. Another is looking at a kind of observing fields that would be of particular interest to a broad community. You may have already discussed this on a future hangout, but we have a whole series of images now called the frontier fields.
Mm-hmm.
These are deep space images that have many galaxies. I don't know if you can pull up one of these.
I just did.
Yeah, that's a good example. So here's a cluster of galaxies. So this was an initiative that was fostered by, if you can go back to that, by the science community and blessed by the director of the Space Telescope Science Institute to use a significant amount of time for Hubble observations of several of these deeper fields that show many, many galaxies, but in particular they have clusters of galaxies. Well, why is this interesting? Well, it turns out that clusters of galaxies are the most massive gravitationally bound systems that we know of in the universe, and they can actually distort space in significant ways because of all that mass, and most of that mass is in dark matter that we can't see. So with Hubble, we can see some of the lit up matter, the stars, but that distortion of space actually distorts light coming from background galaxies in the distance. So you can see these interesting arcs and stretched out features. These are just normal galaxies in the background that are getting distorted by this gravitational lensing effect. And they also get magnified. So we're using these clusters as nature's lenses to help us both study very distant galaxies that are getting magnified by this effect, and also mapping out where the dark matter is by looking at these distorting effects of the dark matter in the foreground cluster. Looking at several of these clusters, astronomers are really getting a better handle on where dark matter is, how it's distributed, and how gravitational lensing actually works, and is also helping us to understand some of these very distant magnified galaxies. I use this as an example of plans that, with the science community actually thinking together with directed committees considering how best to use Hubble, ideas like this can come forward where we actually dedicate part of Hubble's time to doing observations that we will be grateful we did in the future, and that also prepare us for complementary work with the James Webb Space Telescope. We are convening another group now of astronomers that are advising the director of the Space Telescope Science Institute on what more we should do in terms of observing Europa. I mentioned earlier the kind of intriguing observations with Hubble that show potential water vapor plumes on Europa. That gives us a potential way of studying the oceans under the ice, initially by looking at water that may be expelled from cracks in the ice. So what more should we do with Hubble while we still can? So we are doing several exercises with the science community, studies to understand even what kind of fundamental physics, what kind of fundamental astrophysical questions do we want to address with Hubble while we still can. We don't know if we have just a few years or quite a few more years. It's a little bit uncertain, but we want to make sure that we get done the most important science while we can, while we have this capability. So that's the science angle of planning for Hubble's future.
Well, I'm excited that I have faith in Olivia and her team. They're gonna keep us out there. They're gonna keep Hubble out there at least another 10 years.
I just wanted to mention something that Jennifer made me think about, is that also astronomers are very well organized in that every decade we have a review of the science that we want to do and what capabilities we need. We need to do that exercise in 2020. We're only 3 years out from that. And so people are already starting to talk about what these things that Jennifer's talking about for individual telescopes like Hubble, but then the whole landscape of where do we go in astronomy in 2020 and beyond. And Hubble, James Webb, and WFIRST will all factor very strongly in those plans.
Right. So this is the National Academies of Science does this every 10 years. And it will factor in what will we still be able to do with Hubble in the 2020s in conjunction with these other observatories, and that feeds into their recommendations of what kind of future observatories, both on the ground and in space, that we need to answer the most important questions before us in astronomy and astrophysics.
Okay, well, I'm running, things are zooming by, and I still got to get to a lot of questions and comments that I see. But I just want to bring this up because it came out this week that there are some ideas for possible servicing missions for the Hubble Space Telescope. Other people are thinking about these things, and there was an article in the Wall Street Journal, I think, that came out on talking about plans that may be in the works for another Hubble repair mission that could be launched. Can you guys maybe comment on this just very briefly?
Yeah, I can say a few words. So Hubble is the exemplary mission of how a science mission and astronauts and ground-based engineers and even robotics can all work together to make a very successful mission. So with these multiple servicing missions we've had over the years, we've demonstrated how valuable it can be for humans and satellites and science to work together to keep a facility like this at its peak. And so there are, of course, ideas out there in the public and innovative thoughts of how we might service future telescopes, or possibly service Hubble again, or even construct future telescopes, larger telescopes in space. These are just intriguing ideas that I think have been fertilized because of the success of all the Hubble servicing missions. We don't have any plans at NASA to do another human or robotic servicing mission at the moment. So we are doing what we've just described, and we're doing everything we can to keep the Hubble we have operating as well as it can, as long as it can. And the future ideas that are being generated and bantied about, those will be considered by NASA and by our advisory groups like the National Academies, as they consider what kinds of things we ought to be doing in space astronomy in the future, and what would be the highest priorities, and what are the technological capabilities. So while we're not formally planning a servicing mission for Hubble right now, it's very interesting to see these ideas kind of organically being generated.
Yeah, and you know what I think, Jennifer? I think we're going to see a lot more stuff like this in the future. Hubble is so beloved. I think that as time goes on and technology, maybe commercial interests, all of these things start to become more viable, I think we're going to start seeing a lot more ideas like this in the future. And it's good that people are thinking about it. But yeah, I wanted to get your take. NASA isn't necessary and has no plans to do anything right now. But these ideas are out there, folks, and a lot of people are going to always be thinking about them. I am out of time, but I want to please read some of these questions and comments. And if you guys, I try to be very respectful of your time. If you have to leave, I completely understand. But is it all right if I just read a few questions and comments? Maybe go a little bit longer than an hour. Is that okay with you guys? If you have to leave, I completely understand.
We wouldn't think of leaving.
Wonderful. Thank you. Well, John, thank you very much. So John Suffel is asking on the YouTube chat window. I remember NASA once asking for old 286 and 386 processors to replace those in satellites designed in the 1970s. What processor does Hubble use?
I'll hand that over to Olivia.
I'm sorry. Could you repeat the end of that question?
What
is the question?
processor does Hubble use? We're talking
we
about
have
being built in the 70s.
Yeah. Actually, yes. We have the payload computer, the NISCI. We call it the NASA. It's a NASA space qualified computer that was actually designed and used by many different spacecraft in the 70s and 80s. And we, in fact, have that computer on board the Hubble to control the science instruments and pass science data to the main computer, who then passes it, down to the ground, or, puts it on a tape recorder. So, yes, our main computer is a 486.
Get out.
And that's the main vehicle computer. And each of the instruments have processors, 386 processors in each of the science instruments. So we have a lot of processors, but the ones in the science instruments and the main computer on board the Hubble, they're much newer than 70s technology that we have in the NISCI computer.
Okay, well, Alberto's holding up his phone like it's more powerful than
yes.
You're muted, I think, Alberto. Okay.
Underscores the value of servicing, right, and bringing up new technologies to.
That's right. That's
exactly
right.
Yeah.
Felipe Meza is asking, are those gyros similar to the ones used in Kepler or K2?
Oh boy. Honest to God, I don't know the answer to that.
Well, now Kepler has a slightly different issue, because it was designed to point in one spot in the sky, and the reaction wheels that allow it to do its science, sort of two of them stopped working, and so they use the radiation pressure from the sun as one of the gyro wheels. So it had a slightly different mission, but I don't think the hardware is all that comparable between them.
Right. I suspect that's the case, but I don't know the answer to that. I can send you email and send the gentleman who asked the question email.
Okay, so George Caldwell, welcome, George. What is Hubble's maximum longevity? Now, you mentioned that you sort of run these statistics and these what do you call them? Forecasts.
Yeah.
What's its maximum? All bets are off.
Right. Well, it's
Hubble
very
won't be up
difficult.
there
Like
anymore.
I said before, there are many subsystems on Hubble that are very old and have been operating for 27 years on orbit. And so we have to keep that in mind when we talk about these over 90% probabilities of the Wide Field Camera 3 still performing beautifully in 2025. Okay? So, I mean, you look at the components separately, and I guess our fine guidance sensors are a risk item, but we're still seeing in these very coarse estimates of longevity, we're seeing the mid-20s for still some capability with Hubble. I don't know how much capability. I don't know, how much compared to what we have now, which is at its peak. But we're still looking past 2020 to the 2020 mid-20s.
Okay. So I asked you guys at the beginning of the Hangout to give me some comments on what your favorite Hubble science was, your favorite Hubble image. I'm going to start with Zolt, actually. Zolt, since 1983, you've been at this. And so you've seen roughly every image taken from Hubble. What's your favorite?
Well, it's hard to pick out just one, obviously, but one of my favorites is NGC 1300. That's one of the images I sent. It's this prototypical barred spiral galaxy. So it's a magnificent image with this just, sort of classic design to it. But if you look closely at the image, it also exemplifies some of the great strengths of Hubble in being able to see with with the high resolution. You can pick out these regions of star formation and these dynamic spiral arms. You can look way down into the core of the galaxy, see these dust structures way down deep in the core, which also touches on the dynamic range of the sensors to be able to see the very brightest parts of the galaxy as well as the faintest parts that we can see. And also, if you look outside the galaxy, beyond the galaxy, or even through the galaxy, you can see much farther structures away. You can see very distant galaxies through this image. So in this one image, we're seeing the whole scope of, in a sense, we're seeing the whole scope of the universe in one image.
Okay, and so what about you? Carol, come on, you got to tell us which one. You got a favorite?
I do not have a favorite.
I
love my standard answer is the last image we produce. I mean, I mean, they're all fabulous. The one area that I like that I'm in the minority in some respect is I think globular clusters, and I didn't send any images in, but I think globular clusters, and they all go, oh, really? Yes, because globular clusters are the things that actually do show the resolution of Hubble. But also the fact that there are tens of thousands or hundreds of thousands of stars in one object that all form together. Individual stars that we learn a lot about our nearby neighborhood as well as the distant universe. They're my favorite, and I did research on them, so I like them a lot. But I mean, I can look at the whole gallery of images, and each one I'm like, wow, I like that one too. So hard for me to choose.
Yeah. Well, for me, what about you, Alberto?
I put up a global cluster from Carol.
Oh, there we go. Yes.
Which is
Yay!
which is quite impressive, I think. No, I have a bias toward, again, probably it's because of the research that I used to do toward, the earlier universe. So I think my first paper was on the Hubble Deep Field, the original one in 1995, which kind of struck a note with me. And lately, actually, those images have been surpassed, in my opinion, by what Jennifer and others mentioned, which are the frontier fields, right? These images of the deep universe that tell, they use Hubble beyond this, basically is built-in capabilities, if you will, making use of the geometry of a universe. So very deep images are the ones I love. So.
That's I think anybody who knows me knows that's my favorite as well. But I also love the fact that the frontier fields are able to make Hubble more powerful than it ordinarily is by using these gravitational lenses to sort of bring in galaxies that Hubble can't necessarily see on its own. Jennifer, what about you? You got a favorite? You're muted.
I wish I could be more exciting and innovative and think of something to tell you that other people wouldn't, but I just have to admit my favorite image is the ultra deep field, and it is the favorite image of many, many, many people. But in fact, if you can put it up, I sent that in here. But anyway, the ultra deep field is, I never get tired of looking at the ultra deep field because every one of those little blips of light is a galaxy. I mean, there's 2 or 3 foreground stars, but everything in there is a galaxy in this little drinking straw area of the sky. And you imagine that extrapolated over the entire sky. That's the universe we live in. And I try to imagine our Milky Way being just one spiral. If we could see it at a distance like this, it would look like one of the spirals in the deep field. And then there's, of course, that third dimension. Some of these galaxies are much more distant than others. And of course, astronomers are spending a lot of effort trying to tease out the distances to these galaxies and really look at the differences between the earlier galaxies and the ones more nearby in space and time. So it's a time machine. So this image is not only amazing just for its content in terms of the number of galaxies, but it's also a time machine right there before our eyes. So I would have to say the ultra deep field is my favorite field. And I also like the zoom in imagery that Zolt has produced. So if any of his zoom ins, both for galaxies, but also he has a nice zoom in for like the Orion Nebula, those kinds of things I think are incredibly helpful. So
yeah, those are very
that's
beautiful.
my vote.
Okay. And Olivia, how about you?
Yes, if you could put up the Butterfly Nebula, which Zolt provided you. It's the pink nebula.
I also sent it too, so there's lots of choices.
I think Jennifer sent it,
Yeah, there.
Or Jennifer, I'm sorry, Jennifer.
Hold on, I'll put it up.
Okay. Well, what you're going to see, this is I agree with Jennifer, the deep field, of course, but this also is one of my favorites. It's of a dying star. And yes, you can see it there. And the star is in the middle of this hourglass shape. And I just think that the detail, the resolution in this image is breathtaking to me. The star is illuminating the gas that is coming out of the poles of the star. That's why it has this hourglass shape. It's shaped like this because of magnetic fields associated with the star. And it's the ultraviolet light is illuminating this gas, and some of this gas is moving out at incredible speed, on the order of 600 miles per hour, for example. And I just think, the way Zolt has properly combined, you can see hydrogen is the pink, and there are many other elements you can see in there. So that's my favorite.
Okay, well, it looks like the winner on the chat window is definitely the Hubble Deep Field as well. A lot of people want more Hubble Deep Fields, and to be honest, the Frontier Fields did just that. They took 6 more the Hubble Deep Fields. They're calling them parallel fields. They looked at the galaxy clusters and the galaxies behind them, but they also at the same time imaged an area adjacent to that area of sky to see if the Hubble Deep Field was the same in all of these other fields, like were there the same kind of galaxy distributions and things like that out there. So the Hubble Deep Field, has produced 6 more of those. They're calling them the parallel fields. Okay, a couple quick comments. Hans Milling, is it plausible that they will do a service mission when the telescope fails to operate? Must be a lot cheaper than to build a new one. Also, because Hubble is so strong in the visible light, it does seem to be that the visible is taking a lot less of a what's the word? That's center stage anymore. Now we're much more interested in these other wavelengths, right, Jennifer? We're more interested in, say, the infrared and ultraviolet, but visible, not so much these days.
I wouldn't say that, actually. I think actually we're doing a lot of good work in the visible, on visible light with Hubble, and we continue to. That's Hubble's major strength. So we are continuing to take advantage of the extremely high resolution, crisp images we can get in visible light ranges with Hubble that really, in many ways, are unparalleled yet by other telescopes. So that, in addition to the infrared and the ultraviolet capabilities of Hubble, it's all being used heftily these days. Yeah.
Okay. George Caldwell's asking, considering what Hubble has achieved and all the ways it has surpassed our expectations, JWST certainly looks very exciting. Will Hubble and JWST produce composite images in different wavelengths? That's a good question.
I think the answer is definitely.
Yeah.
That's an obvious thing to do, right? Now, what the quality of those images will be is yet to be determined. But there'll certainly be images produced, visualizations produced from JWST data exclusively, from Hubble data exclusively, continuing, and combinations of those as we produce images that are composites of multiple wavelengths today, from, as I think somebody already pointed out, the other great observatories, Chandra and Spitzer, and even ALMA ground-based telescopes. And we use whatever we can and produce whatever we feel produces the best visualization to tell a story, basically.
Yeah, I mean, we mentioned that we have very specifically a combined program for scientists to propose to use both telescopes for the astrophysics they want to do. So the expectation is that, yes, they will take imagery, and yes, we will produce the beautiful composite images and compare and contrast them.
But you don't want to just do it, do you, Carol? I mean, there needs to be a science reason to have both of these telescopes.
That's what I'm saying. There will be proposals to do that, and we'll take advantage of that.
It'll be interesting. It'll be interesting.
It'll be fantastic.
All right. Okay. Well, there was another comment. I scrolled past it, but the comment was, "Is this Hangout available in podcast form?" And the answer is, this one will be yes. This particular one, I'm going to be posting the audio from on our Twist podcast, This Week in Space Telescopes, and that'll be posted next week. You can subscribe on iTunes, So yes, but not all of them, because we want to, the ones that are relevant to space telescopes, we sometimes repost on that podcast. I am considering doing a deep astronomy podcast where I do the audio from these as well. If enough people think they want that, then let me know with some comments in the description box or comments below, or send me a PM or something and let me know that you'd like to do that, and I can look into doing it. Okay, we've gone over. I've got to stop it here. It's 15 minutes past. I want to thank my guests, Dr. Olivia Lupie. She's the HST Science Instrument Mission Operations Manager. Dr. Jennifer Wiseman. She's a senior project research scientist for Hubble at Goddard Space Flight Center. Dr. Carol Christian. She's the Hubble Project scientist for outreach at STSCI. Zolt Levay, Hubble image guy extraordinaire, awesome guy. Thank you for coming back, Zolt. And of course, my good friend, Dr. Alberto Conti, the innovation scientist at Northrop Grumman. Thank you all very much. Thanks for taking time out to talk to our guests. We hope you'll come back to talk more about Hubble as new developments happen, as new things start to happen with Hubble. We hope you'll come back, because this has been awesome. A lot of great comments.
Tony, can I just mention that people can hear all about it and see all about it at nasa.gov/Hubble as well.
Thank you for that. Okay, so definitely go there. Oh, one more thing. On Twitter, there's this thing called Hubble Live. Did you guys know this?
Yeah.
Where it actually tweets at you what it's looking at any given time. It's really cool.
I was going to mention
Hubble
that.
Telescope
Actually,
tweets.
Yes. And Alberto and I started that project a long time ago.
It's so cool.
It was revived, and we now have a Twitter feed for that. It's great. And you can also see some of the images and understand on Facebook where it's looking.
Yeah, no, so yeah, it's really, I love watching it, because it says, I am now taking a bias calculation for, and it says who it's doing it for. It's really funny. So check it out, follow it on Twitter. Thank you all guys very much for being on our hangout. This was an awesome one. Thank you guys all for watching, and as always,
keep looking up.